could be the result? Is there going to be a theory, and what could be the limit? Now we have quite a good proof, a good idea. So the main technique is, well, the technique is completely changed from the original theory. But in fact, with the new method we implemented, we can prove results in the classical averaging theory and prove stronger theorem there. So I will be talking about this now. So to start with, what is stationary Markov process with invariant measure mu? We define average, we represent the average of this function by a bar over it. And so that's the equation I wrote down informally like this. And here is that's the fraction Brownian motion distribution derivative. Now, I think behind the averaging theorem, there's a static theory. The static theory is quite simple. Suppose your f doesn't depend on slope variable. So your whole theory become averaging theorem. You look at 0 to t, f of ys epsilon ds. Now, what does that converge to? And that's just simply a continuous version of law of large number. And but because the f is wrapping around the process, is functional law of large number. And so here we look at the law of large number rewrite it because we have this way to write it down. And this process, this guy converge to t multiply f bar. That's the average. And this would be, as epsilon go to 0, this go to 0. This we call the functional law of large numbers. Now we wanted to hold for f in a suitable class, regularity class, depends on what problem we are looking for. Yeah, so what I'm saying is if we look at the x doesn't appear in the right-hand case, it's just this guy, you change it, change the time is that one. Now, if this f bar equal to 0, we look at the central limit theorem by rescaling this a little bit less. So we look at this object, and this converges to a Brownian motion. So that's a functional CLT theorem, central limit theorem to a Wiener process. If it doesn't converge to a Wiener process, we sometimes call it functional non-CLT. So the theory is really this static theorem. The first one gives you averaging theorem. The second one gives us the homogenization. But you have to work. So this, in over many years, people just try to find the best way to put through such a theorem, and painstakingly cut off your interval and approximate and approximate and approximate. Now, what happens is there's a few development. One is a rough path theory. It's called continuous theorem. If you treat this guy as a rough path, if this guy depends on parameter that converges in the rough path topology, the solution converge. And so that's basically also come from some sewing lemma, and we use some stochastic sewing lemma to work with that. And that allows you to remove all the painful computations in one go. And also give us some understanding, something we couldn't do before. So I'm going to give you a toy model in a paper Martin and I wrote, the first paper we wrote. So it's averaging with some raw path tools. Essentially, we just use stochastic sewing lemma and sewing lemma. So in this theory, sorry about that. we would assume the Y process is strong mixing. Basically, if you look at the algebra of Y from a certain time before T and another time further away, they get more and more independent. So this coming down to this inequality. Take a function yt, g of y as bounded measurable functions. This correlation is decaying t minus s to the minus delta. And here's the infinite norm, control it. In this case, well, we can take f bar being bounded. Otherwise, I just remove a bar. That will be the averaging theorem. So I take this to make life easy and compute its variance. So the first thing to do is compute its variance. The second moment. You do a change of variable and plug this guy in. So unwrap the f and the g, and so you have f squared come out. And this coming here, you integrate, you get t minus s 2 minus delta. And this little bit epsilon delta come out, and that's very good news. And that's a little bit hold continuity. Now, that's the basic essential ingredients come from the ergodic state. And so with a bit of work, you can have a p moment estimate. P moment estimate is very good. It allows us to have a uniform estimate in ST and so on. So back Homograph theorem. Now, here's a theorem. Suppose Y is what we think it is. And your F is reasonably, Y is sort of a uniform Lipschitz continue in the first variable. Remember, we want to approximate, consider slow variable being constant. So in that case, that means I have to have some continuity in the first variable. But second one, we don't assume much. And then this fx y dot over epsilon converge to the average f of x. I miss x here. They converge to that in a certain topology. The topology is this, you allowed to averaging over your function, so that have a regularizing effect. The regularizing effect, if f is nice, give you t minus s. But if it's not nice, you still have something. What we have is 1 minus kappa. So this hold continuity minus kappa. Kappa is positive in time. A little bit of positive continuity, C gamma in space. So this gives us such a theorem. Now, why is this useful? So from here, we can look at for two different, say you have your slow variable at two different times, and we can look at this P norm. You get an estimate like this come in. X minus z come from Lipschitz continuity. Okay, by this stage, we rearrange everything. And we put the time factor on the other side. That's the C minus kappa norm. And we put the xz in by Homograph property. So we get some hold in x. And then we basically look at this object, found out is in the C minus kappa gamma topology. Almost surely you have this error bound epsilon. Now is how to put all of this together. So the toy model is the following. Now I'm going to, we have a differential equation and we have this estimate. Now my x is moving. What we do is consider x. I know a priori what x look like. X is going to be in this B alpha P class. So the LP norm of that with a bit of a time hold continuity there, and then that's finite there. So I take an arbitrary object, not the answer, but arbitrary process in, and we look at the to define this process. So X in principle is what the solution going to be, but we take it static. So we want to show this is converges. And F is quite weak, is C minus kappa in time. And so under some technically, we could construct this integral by sewing up this integral. They look the same, right? But this integral I interpreted differently because fraction Brownian motion, as in yesterday's talk, we seen is a transformation of a Wiener process by a fractional kernel. So it's an integral of fractional kernel against the Wiener process. Like in Mandelbrot, Van Ness paper, you could decompose into two parts. At any time, you can decompose into two parts. One part is smooth, the other part is adapted, and they're independent of each other. So using that, so one part adapted, we use the Wiener measure, we integrated, and the smooth part we consider at the Riemann-Stichter integral. So this allows us to sewing up this to get an integral. And now once we've done that, we constructed, we see this integral to the, I repeat, the integral against this fraction Brownian motion is controlled by the integrator in the minus kappa gamma norm. And with some parameter here, this means that if this guy is small, I'm going to have convergence. So I turn the convergence of fraction integral into the convergence of F, the integrator, in that weak topology, very weak topology. Now, to finish this up, there's a theorem here I think could be very useful. If you take Fn, so the F0 here, to be, well, C zeta, so that's a C2 in the second variable holder in time. And you look at the solution for this, I'm taking h bigger than half. So I take a zeta plus h bigger than 1. So this is Young integral. We look at this has a solution. And we look at the average. The average is going to be nice, smooth. So this one has a solution. And the theory is suppose the coefficients converge to that coefficients in this very weak topology. After you average it over the path, you don't do pathwise, point-wise convergence in time, but you average it, you get it convergence, then the solution converges in probability in C alpha. Now we can put it together to give a theorem. And this is what we call the fractional averaging theorem. So if we have FG being usually nice, BC2 for this type of equation, then the solution X epsilon converges to the average, the solution to the average equation. Now I'm going to look at that theorem a little bit more in detail in the static case, what it means. Remember, if we have Wiener process, this one is martingale. To show martingale converges weakly, we only needed to say the variation, which is S to T F square YR over epsilon dr converge to that. That we already know, it's law of large number. So we know that's true. Now we ask the question, what happens with the fraction Brownian motion? What we just proved, maybe a little bit more, not what exactly we proved, is this guy converged to F bar, multiply the increment of the fraction Brownian motion, and it converges in probability with the rate epsilon kappa. Now, here's a note. How differed this from a classical theory? Now, classical theory, there are two. One is you don't have noise, and that's dt. I have a Young integral. That means that for every omega, we have an equation. So I can, for every omega, every realization of my fraction Brownian motion, I have an equation. Now, the correct theorem to think, if you have that, could I say fix that realization to converge in probability? And that we couldn't prove. What we proved is it converges in probability, but I have to consider the randomness comes from fraction Brownian motion. So if you ever work like a random walk in random environment, they have a name called quenched convergence or annealed convergence. I would say this is an annealed limit, and we have no idea whether Quench's theorem works. So there's lots of nice problem to work with, and this we don't know. Even at this, with some people in my group, we work and try to see whether this works for a fixed realization to say this converges. You see, this randomness here, assume it's independent of the other one. We have really not too much idea what happens where this converges. In quenched case, as I said, the technique is tightness. And there's a result for this on the feedback model. Our results are very basic, just trying to see what's going on. And the assumptions, we were not aiming to make the best possible or to see what is really the correct assumption. We just put a simple assumption and make it work. So that's that result. Let me see whether I have time. So that's the h bigger than a half case. I think I have to speed up. So what then we have, the second paper we are with Martin Era is for the h between a third and a half case. And that one troubled us quite a little bit. For fraction Brownian motion is the regularity of the sample path is just a little below h. The larger is h, is more regular. So h bigger than a half, you get Young integral. H smaller than a half, you use rough integral, more of a sewing up the theory. And so for h bigger than 5, you have super diffusion, otherwise you have this subdiffusion. It's rougher for h smaller than a half, and more difficult to get the integral. So here I set up our assumptions on the Markov process on the fast motion. Again, this is we just put whatever we think is simple, easy, and we can see what is going on. So we put a spectral gap theorem. For example, you can have elliptic diffusion on the compact manifold, uniform, and so on, so that you would have a spectral gap. And that gives us some nice, one thing we need is some kind of a, correlation. If you average correlation, what you get, and that's useful. So that's where we are for setting up. Now, for h between a third and a half, we made a sanity check to see whether that's going to be convergent. So this case, the difficulty would come from G. We can try to forget it, that part. And so we take the Brownian motion part. Suppose Y and B are independent. This is just a Wiener integral. We can treat it as Wiener integral. And the variance, we just, it's a two integral, you put it together. bring the expectation in. And because it's fraction Brownian motion, not a Brownian motion you just have S equal to R, that's it. Fraction Brownian motion, you have to bring in the second derivative, derivative once in S, once in R, the correlation function, which is 2h minus 2. Now, what the difficulty usually comes from fraction Brownian motion, you see the singularity here. When h is smaller than half, you have a singularity at 0. And if h is bigger than half, you have some singularity at infinity. So you now change the variable, you see the a little epsilon come out, and then we have this function. Thinking about f being bounded, that tell you what is the best order in epsilon. The best order is epsilon 2h minus 1. And that blow up because 2h minus 1 is smaller than 0. So that means this result is not going to hold. It's not going to hold, we're going to scale this one, we're going to multiply by epsilon 1 minus h in front of the equation, okay? So this is what we're going to do is rescale this equation and try to solve this equation. That's the correct scaling. It turns out that this is for dealing with the h between a third and a half. It turns out that when h bigger than a half, we had an averaging theorem. And it turns out it actually still works if h bigger than a half, as far as you get rid of the problem at infinity. To get rid of problem at infinity, we assume f is centered. You assume a centered function, and then this theorem works. So essentially, this is a fluctuation theorem around the fractional averaging. When the fractional averaging is trivial, that's what the h bigger than half is. Now let me, I don't think I have much time. I would say if h equal to half is the stochastic averaging, h equal to 1 is homogenization. So you have the theory I reviewed. And this equation itself is not easy to reinterpret because the randomness here. What we do is approximate the b by a modifier. So that's the equation after modification. And we take delta go, so we can take a delta go to 0, then epsilon go to 0. And that's what we're looking at. So this is the theorem between h between a third and 1. And this theorem said the equation we just talked about would converge to this SDE, Kunita type SDE. So you have this is a Gaussian noise. And this is a function comes from correction of raw path. And this is averaging of the drift. And the Gaussian random field has this correlation, is wet in time, has a spatial correlation like this. I'm going to give you the formula for sigma. That will be concluding my talk. So in this case, you note I say stochastic flow converge. Normal averaging theorems take it from initial condition, you look at solution converge. Here, with each simultaneously coming from a finite number of initial point, the solution converges simultaneously. That's the new one for averaging because it's too difficult to track your initial condition. But this is because we use some theory from a raw path, you get it for free. And now this is the formula. Take the bit between before Brownian motion. The Brownian motion has a key component, that's the Fk. And we apply the fractional operator to Fk and average this out in Y. And so this is the coefficients. Now, it's good, this is the definition for fractional derivative. Take the kernel, apply the semigroup PTF, which is the semigroup for the y variable, integrate out for h smaller than half. For h bigger than half is not quite right. We have to remove the average out. So that's now what it is now this is the what come in quite pleasing. We're doing fraction Brownian motion. For h equal to half, this formula exactly agrees with the stochastic averaging formula. So you take the square of the function you average. For h equal to 1, it agrees exactly the homogenization. Homogenization, you usually have a vector field which averages to 0. And then you say you have elliptic operator with you can solve a partial equation, and the solution partial equation you put here, then you average out. So that's the homogenization theory. So in terms of ends on the result, we collect them together into one unified formula, essentially unified approach, because they have not complete the same proof yet. Okay, so I think I'm probably done. Yeah, so I just try to finish the hour. I start 2 minutes late, so I just say this is some. So this first you have some interesting, if you ask Calorie, interesting central limit theorem for this one in C alpha. Idea of proof is lifted to rough paths on function space, infinite dimensions, and then construct rough drivers and proof tightness, which is a bit of hell of work to do. Okay, I want to finish my work with how do you reduce from a perturbation mode to separation scale. The reason I want to talk about it, because this is very strong in Unicamp, and many people been working on this, so I want to pay a bit of tribute to this. If you have SDE with a small parameter, you want to separate the slow and fast. What you do is take the epsilon part equal to 0 to see what qualities here is function of ZT. Is there a quantity is invariant on the Z, or whether it's symmetry. A number of things to do. So typically you could have an energy function, momentum, and you could also have a map, a submersion from one manifold to another manifold. And typically the projection would be a slow variable. And typically you could have talk about a manifold with isometries, which is a homogeneous manifold, or principal bundle, as Martin been talking about, with action by a group, and then invariance by the group. And also you can talk about the orthonormal frame bundle. Now, so there's lots of people from Unicamp been working on sort of a decomposition of a solution and averaging on Brownian motion. Not many people do work on. There's also an Italian group, French. There's a group who worked on manifold. There's a few people, and these people did a reduction of the time symmetries, I think. Now, with this, I'd like to thank you for listening.
Thanks. Questions? Comments?
Thank you very much. It's probably a very naive question, but is there any sense of if it could be useful, these techniques developed by Peccati, Noala, based on applying Malervan calculus to this type of equation?
We do use them. For example, okay. In the work with Johan and also one with Johan and Julia, we have to make we have to prove convergence. So the technique is you prove you have a central limit theorem. The standard theorem is you prove convergence in distribution. Johan and I we are the first one to prove a convergence in Holder topology. Now, what does that mean? Holder topology in one dimension already give you a convergence in raw path topology. So I can use the continuity theorem from raw paths and to prove homogenization. So you could, end of the day, we could have a central limit theorem for iterated integrals. And that means converges CLT in rough path topology, give you everything. To do this, there's lots of computations. You have to work out the convergence and each component, joint convergence. For that, we use something like whether some convergence and they have a correlation, when do you converge it to some water object? So use a theory like if you use things in a certain QC expansion, if that contraction converges, then they would converge to independent one. So this is from Malevin calculus. And so we also have to work out some Malevin derivative technique to control the moments. So they are used. The Malevin calculus are used.
More questions? Then let's think again. See? I need to correct the information about group picture. You'll be tomorrow because the weather is not so good today. Then we change to tomorrow. Group picture. Okay. Maybe.
Oi. Já está lá.
Você não vai estar mais? Ah, é, não, não, a carta é mais prioritária. Não. Não, amanhã não vai dar para tirar foto, não. Pois é. Ué, a gente vai na carta de fotografia, mas importante porque eu falo da FAPESP. Por que não faz a foto hoje mesmo e amanhã faz outra? Eu também. Aí depois você escolhe qual que você vai. Faz uma montagem, né? Aí que nem os funcionalistas. Não, eu acho. É que eu não sei se acho que eles mandaram para a FAPESP, né? Acho que eles não chamaram. Um fotógrafo que vinha tirar foto. Isso aí era no canto, né?
Let's start. Acho que podemos, né? Luiz Renato.
Eu mandei para você a mensagem da do
quê?
que diz direitinho da foto da capa.
Ah, tá.
Mas é a da Helena. Começa 9h30, mas a leitura é às 11h, que vai fazer longo, vai São Paulo. Vou mandar.
A gente pode, de repente, fazer no meio das duas palestras. Ah, não. Não é duas palestras.
E amanhã eu não, estou fora.
Luiz Renato.
Dedicado à luta pela democracia.
Vamos começar? Acho que já dá no horário, né? Já está o horário. Okay. Let's start again. It's a pleasure to introduce Luiz Renato Fontes from USP. Thanks.
Hear me? Can you hear me? Yeah, okay. Thank you, Adriana. I'd like also to thank Christian and all the organizers of this very nice meeting and for putting this together and also for inviting me to participate. It's very nice to be back in the flesh. I'm going to speak about the contact processes, the contact process. I assume many of you don't know much about it, so I'll explain what it is very briefly. So this is a process that was introduced by Harris. It's a model for, you may think it as a model for the spread of an infection. And so it works more or less like this. So I'll explain it in a picture. So we have a graph. So a connected graph, you can think about, for most of the talk, it's going to be ZD, but it can also be other graphs or even finite graphs. But in most cases, it's essential that it's an infinite graph. But in any case, you have individuals sitting on the graph. They are static. They're just sitting there, one individual per site, and they can be even either healthy or sick. If they are healthy, it's all right. If they are sick, they can transmit the sickness, right? And the transmission is done through these contact bonds, okay? So you have a structure like this. Over the sides of the graph, you have timelines for the individuals, and you have these contact bonds, which you can think appearing on timelines for the bonds of the graph. Okay, so have timelines. I'm not depicting the timelines for except for this case here for the bond ZW. I'm not depicting the timelines for the bonds. Okay, but you have timelines for the bonds, and on the timelines of the sites you have these marks, these crosses here, and along the timelines of the bonds you have these also these dots here, which over which you put the contact bonds. Okay, so in this structure you have the spread of the infection, right? So the probability distributions here are things are over the site timelines. You have these crosses which appear according to a renewal process. So you have these variables C, which are all IID, and over the bond timelines you have Poisson processes. Okay. I mean, you could put also the variables here, but they would be exponential, right? Harry's many or most of the works about this model, for most of these works, T is also exponential, okay? And we depart a little bit from this picture by allowing T to have a general distribution, okay? So And these the Poisson process for the bonds it has rate lambda, okay, and this lambda here will vary, okay. So the larger the lambda, the easier it is for the infection to spread. So let me just tell you how things work. So how does what's the mechanism for the spread of the infection? So suppose you have this individual here at y sick at time 0, and then it stays sick up to some cure time. So these crosses here, they mark cure times, healing times. If the individual is sick right before this time, it gets healed, right? Otherwise, it remains healthy, right? And it can spread to the sickness to the neighbors. Okay, so you have these infection paths here. So in this picture here, I'm excluding this picture. This dashed bond here is excluded. Okay, it's absent. So there's no infection crossing these bonds, but it crosses the other bonds. So you have 3 infection paths in this picture, and I highlighted here one of them, this in green. But you have actually 3 paths. Okay, and they all stop right after some time. So before time t, all of these infection paths here stop. So at time t, there's no effect. So I'm supposing here that y was the only infected guy at the beginning. So the infection dies out before time t. Okay, so at time t, there's no one left sick. So this is a stationary state, right? As soon as everybody's healthy, there's no spread of the infection. Okay, but if this bond were present, then we have the previous paths, but now there are extra ones, and these. So we have a continued spread of the infection. So at time t here, we actually find we find some people who are sick. Okay, so in this case, for this configuration of crosses and bonds, the infection has survived up to time t, starting from y. Okay. And this model. So this is how the model works, and so this is a model that exhibits phase transition. Okay, phase transition with respect to the occurrence of eternal survival. Okay, so you can ask whether the probability for this survival of the infection, starting from a single individual to run forever, is positive. Okay, and so this model it's a bit like a percolation. So actually, it is related to oriented percolation. Okay, so in this picture, of course, the graph is z, or I mean, you think of it as part of z. So think of this as going on at every site in z. So this model would be then related to oriented percolation in 2 dimensions, right? Because of the I mean, the orientation comes from the time orientation. Okay, so in percolation you would have to have it in 2 dimensions with. Okay, so this reasonably popular model, many works in the literature. So I just mentioned 2 names here besides Harris. It's early contributors, and I mean, they also wrote accounts, texts, including this results about early texts about this model, which you can consult. Of course, there are many other more recent things. And so in our formulation, let me just tell you that, to the best of our knowledge, this is a sort of, nobody had looked at that before. I mean, these general inter-Q distributions. But I mean, you can more or less see that it has the flavor of some earlier work which considered the Poissonian cures. I mean, as originally formulated by Harris, but with random rates for the Poisson processes, and depending on the distribution of the rates, you can have you can have effects that more or less corresponds to what we are going to show you. I'm going to show you in a second. Okay, so but let me not dwell too much on this relationship. I mean, feel free to. I mean, you can see discussions about this in our papers. So, but what's the question we want to address? So the usual, or the first non-trivial question that one asks about this model is whether there's a positive probability for the infection to survive forever, right? So, but we want to so typically what goes on is that you require some positive lambda for this to happen, okay? So the question we want to ask is whether this probability can be positive for all lambda, okay? For all positive lambda. So this is something that doesn't, oops, sorry. So that doesn't go take place in the usual original model, okay? Where the distribution of the intercure distribution is exponential, okay? So in that case, there is a, I mean, the probability of survival is 0 for lambda below a certain positive value, lambda c, okay? So, and this is, of course, a very well-known result for people who are more or less in these particle systems. So this is, and the proof of this is comparison to branching, so it's a standard argument. I'm going to perhaps go back to this slightly more general situation later on. And but let me tell you our results. So our first results, a set of results, concern the situation where we have survival for every conditions on the distribution, intercure distribution, so that we have survival for every lambda. Okay, so this is, of course, I mean, once you start to think about it, you quickly imagine that this must have to do with the with heavy tails, right? For the distribution of the intercure. I mean, as the larger this distribution between the cures is, easier it is for the infection to spread, right? So and indeed this correct way to think. I mean, our first result stipulates that if we have a heavy tail for that distribution in this way here, so the tail distribution is larger than t to the minus alpha, with alpha larger than 1, then we get this phenomenon of survival for every, with positive probability for every lambda. And note that in this case we don't have a first moment for the distribution of t, right? So you also need some regularity conditions, okay, for proving this result. And sorry, so here are them. I mean, you don't need to look at them very much. I mean, this is just know that this includes much more regular situation where T is attracted to a stable law with index less than 1, okay? So this is, and more recently, we came up with an example where we can have a distribution attracted to a one stable distribution. But then we require that, I mean, for stable attraction to stable distribution, you need this slowly varying function, right? So we have to impose that it grows quite fast. Okay, it's slowly varying, but other than that, it grows as fast as almost as fast as you can. Okay, so let me not give you too much details, but yeah, we can go to alpha equals 1 with this proviso here. And so let me give you an argument for what's going on here. So a mechanism for why this how this takes place. So this is this is a picture for a situation where T is actually I mean it's a picture that works in general, but well, it's really close to the real argument when alpha. So when the distribution curve distributions are actually attracted to an alpha stable law. So it's not that the general condition that I just wrote. So we have these tunneling events, the sequence of events. They're going to be independent. Okay, so we look at so we were describing here the nth event, and so we already built the. It's a sort of an inductive argument. So we already built the previous events, and so at the nth event you have this xn here, and this Rn bar, which is an increasing sequence, and the increment here it grows quite fastly, so it increases exponentially. And so what you do is you look at the timelines hit by these Rn. So you look at the intervals on the timelines on xn and subsequent ones containing this Rn bar. So the thing is that with this heavy tail condition, you and the usual sampling bias phenomenon that takes place generally on Renault processes. What's going to happen here is that these intervals to the next cure and to the up and down here are going to be quite big. They're going to be of the order of Rn here, Rn bar. Okay, so they're going to be of the order. They're going to be exponentially large. Okay, of the order of magnitude of this same order of magnitude of Rn bar. So this is a phenomenon that well, it's a combination of the sampling bias and also the fact that you have this heavy tails. Okay. And so, so it's the order of magnitude. So you just keep looking at successive timelines here until you find one which is twice, at least twice as large as upwards, right? Than this interval here. Okay. So you call this Rn plus 1. And I mean this length here, and then you just ask that you get these staircases of contact bonds connecting these intervals. Okay, and since these are exponentially large, then the probability of you finding the thing is that I mean you don't have to go very far to find this large one, right? Larger one. Okay. It's just order 1 trials. This is just, I mean, it's essentially a geometric search here that you have to do. It's actually a geometric search, but it's with a bounded away from 0 probability of success. So it's order 1 trials, you find it, And then the probability to connect those systems, this is only order one, many intervals, many trials, the probability to find the star case for any positive lambda. Remember, now these bonds here are appearing at rate lambda, but lambda is fixed, can be small, and these intervals have size exponentially large, okay, in n. So I mean, the probability to connect this is exponentially close to 1 for any lambda, and so and then in the intersection of so this is a single tunneling event. When you intersect all of them, they are independent. Okay, so the probability to have them all occurring is positive. Okay, and then as soon as you have an initial interval here infected, you get a staircase of connections to infinity. Okay. So that's it. So this is the simplest case. Then the other more general situations, those more general regularity conditions, it's similar, but a more involved argument is necessary. I mean, it's not as simple, but I mean, it is basically the same mechanism. Okay. So this is our results for the survival with positive probability for every lambda. So let us look more closely. So let's look at actually at another question here related to the first one in the same condition. So heavy tail and regular. So let's look at this so-called complete convergence. So what's going on with the, if you look, let us go back to the picture. So let us look at, so this is saying that the spread is moving to infinity to the right here. No? So let's look what's going on close to the origin as time goes by, gets larger. And so the thing is that, I mean, this mechanism that I described here relies in the independence of these events, right? But I mean, with some more work, and you can, I guess, it's more or less believable. I mean, hopefully, that's you have a mechanism of this infection traveling back to the origin. Okay, I mean, of course, when you want to make this thing travel back, you start to get to see things you saw before, right? So you get correlations, but well, these are very large intervals, so you more or less can avoid what you saw before, and prove that the infection travels back to the origin. Okay, and so at a large time, provided the infection survived. At large times, what you're going to see is that you're going to have the origin infected. Not only the origin, all the sites around the origin are going to be infected, and their intercure intervals are quite large. So they'll stay infected. Okay. So what this boils down to is that. If you look around the origin at large times, either the process didn't survive, the infection didn't survive. In this case, everybody will be healthy. Okay, so this is clear. And otherwise, by this mechanism I just explained, everybody will be infected. Okay, so this is what's going on around the origin. All right. So the store here is the extinction time of the infection, right? So it can be it being infinite means that the infection survived forever. Okay. So we want to say more. I mean, you have a clear mechanism for this. For the looking at this situation here, let us delve a little bit deeper. So what we want to look at times which are, so this previous result here is for large times, but deterministic times, right? So let us allow ourselves to look at times which are not necessarily deterministic, large times which are not necessarily deterministic, but they depend only on the cure marks, not on the bound marks, right? So only on the cure marks, and also on the fact that the infection has survived. Okay, I mean, if the infection doesn't survive, then everything is trivial, right? So if it survives, and now look at look at what's the probability of the site at individual at X will be healthy. Okay, so these variables here, xi, they're indicator variables for the site of X being infected at time t. Okay, so here we're looking at the event that the individual at X is healthy at time t. Okay. So, and we are conditioning on the renewal cures, okay, and also on the event that the infections have survived. All right. Otherwise, it's clear what's going on. Okay. So we want to say something about this. Okay. For times which are not now can be related to be random. So let me try to explain what's going on in the picture. So there are two situations. So in this case, we are. It's important to say here that t for the previous results we had these more general t's, but now we needed to be attracted to a stable one. Okay. So let's, I mean, for the results to work. So then there are two cases, actually more, but let me just divide it to two cases, and then I'll perhaps explain other things later. So let's look at the case where alpha is less than half. So this is the tail of the intercure distributions is particularly heavy, right? So in this case, let us look at this. So let us look at some time and the age of the renewal process, okay, which is this time elapsed between up to time t from the previous cure time, okay? So in a typical deterministic time, this cross here will be far out. You won't see it in this picture, okay? Like I mean, what happens in this neighboring sites, you don't see anything because I mean, close to a cure mark. I mean, you can put yourself close to a cure mark of site X, but then you're not going to see any cure mark close to it. Okay, in the neighboring sites. This is just because alpha is less than a half. Okay, and so you can be close to this. Cure time, but not so what goes on here. So there are two things. So of course, so now you're looking at the probability of these of these. So at this point, the individual at X is healthy, right? Because it has just been cured. Okay. So what's the probability that it's cured at time t? So it depends on what goes on with the contact bonds in this time interval, right? Incident on X, all right? So if there's no contact bonds, of course the individual here will remain healthy, right? So this is a sufficient condition, right? To not have any contact bonds incident on X during this time. But now, but is it a necessary condition? So, and it is necessary if we are in a high probability. If tau is so if we have survival, right? Because if you look at the neighbors, their intercure intervals are huge. I mean, this is just part of them. So T is large. And so, and since the survival has taken place, they are going to be infected, okay? So they're going to be infected. So if there's a bond here for any neighboring sites, it will infect X, okay? So it's so the conditions of having contact bonds here is also sufficient, okay? And it's also necessary, right? And so so that's where you get these expression from. So this is just the probability of having no bonds, right? In the incident on X, all right? So you have 2D bonds, right? From the nearest neighbors, and all of them have to be absent, okay? So this is for alpha less than a half. So if alpha is larger than a half, then what you can find, if you look along, if you start looking at cure marks here and times close by, you will find infinitely often, quite rarely, but you will find neighboring marks which are close by, close together, like this. Okay, and if you also impose, if your interarrival random variables has also this other condition here, that it attributes mass for every interval close to the origin, then what you will find is quite rarely, but infinitely often, you will find this pack of cure marks here in a neighbor, okay, some neighbor. You will find it if alpha is larger than a half, and then this will act as a barrier for so let us put here the bonds, okay. So this picture doesn't have the bonds. Let me put them. So here are the bonds. So it's the same picture, but now with the bonds. So you can have now a contact bond here connecting Y to X, and so so even if Y gets infected, so if you look at the neighbor of Y to the right, it will typically be the intercure for this at this time will typically be very big. And so if there is a bond, in fact, a contact bond from this other neighbor here to the right of Y, it will infect Y. But then this barrier here will, with large probability, will kill the infection before this other bond here can be used. Okay, so effectively, there's no infection with high probability crossing this bond, right? Even if Y gets infected, it will get cured before it can transmit the infection to X. Okay, so you can forget about the bonds in this between these two sites. Okay, but you have to care about the other ones. So typically you have this. I mean, if alpha is larger than half, but close to 1/2. Then you will find this barrier, but not a double barrier, for example. So just a single barrier. So this will effectively mean that in this expression here, you have to subtract 1, right? So in this picture, this argument I just gave you, you have to subtract 1, okay? And then it works in the same way as in here. So that's the refinement. I mean, this theorem here says that this is the wrong, for these special times, this is the wrong thing, so you have a discrepancy. But the discrepancy is coming from this. You have to subtract something from 2D, right? And the refinement says just that you have, as you move from alpha to 1, you reach various thresholds where so if you're close to 1/2, it's larger than 1/2, but close to 1/2, then you find only one of this barrier, exactly one. not more than 1. But if you move closer to 1, then you start getting 2 barriers, 3 barriers, up to 2D barriers. So this then changes this this expression accordingly. Okay, so you get 2D minus 1, minus 2, down to 0. Okay, when you move past these thresholds. So so this is the one refinement. So the other one, just briefly, it's about finite graphs. So this, in the same situation as before, where you have this stable law attraction to a stable law, but the graph is finite, so you can have survival. So generally, I mean, in the usual model, you don't have survival for finite graphs. Okay, but with these heavy tails, you can have. But there's actually a transition. Let me just be very brief about this, because I didn't say anything about the other situation where you don't have survival for every lambda. And so let me be brief about this. So yeah, so you have to have a transition. If the graph is quite small, then you don't have a survival. So survival happens with probability 0, and otherwise, if it's quite large, depending only on alpha, then remember alpha is now between 0 and 1. So this is so you have positive survival positive probability for every lambda. So now it's so when there's no survival, it's also for every lambda, and it depends only on the size of the finite graph. It doesn't depend on the particulars, on the structure of the graph. Okay, so of course, I mean that there's a gap here on the sizes. Okay, but remarkably, amusingly, this gap is not so large. It's less than 1 for every alpha. So this criteria here, set of criteria here, it classifies all the possible sizes, except possibly for 1. Sometimes it classifies all of them, all of the sizes, and sometimes it classifies all but 1. Okay, and so this is sort of this is something we discovered after coming down with these numbers here and then realizing that there are differences less than 1. Okay, so yeah, so we don't have anything about the possibly exceptional case. So let us now move to conditions for having probability of survival being 0 for some positive lambda. So far we had all, except from this last result, we always had the situation that we have survival for every lambda positive. Okay, so this is one condition. That's the inter-arrival distribution has a second moment. Okay, and so when you have this condition, you can so you can set up a sort of comparison to branching, or the standard argument of comparing to branching, or super martingale argument, and the idea is quite standard. So we start with your infected interval. So this is the interval of the origin here. It's times 0. Okay, so this is an infected interval. It stops at the Cure mark. Okay, and then you set up a sort of a branching mechanism for the spread of the infection. So you do this by generations. Okay, so just very roughly, because this is a standard argument. So you have these offspring, right? These offspring intervals. So arranged by generations. Okay, so have this. So this is the first one is the first generation, then second and third, and so I put colors here so that so red is the fourth generation, and so on. So this is all more or less standard, and then so the crucial thing here is that you have to control, in order to control the comparison, you want to show that you're going to have extinction, right? So you need you have to have a control here on the sizes of these intervals, okay, of these infected intervals, and then here you have again this sampling bias mechanism, and for this reason, in order to control the first moment, you need a uniform bound here for this argument to work seamlessly, and for this reason, so in order to have a uniform bound on the first moment, you need a bound on the second moment of the original distribution, right? Because of this sampling bias thing, right? So this is, and this is also, this is a sufficient and necessary condition, okay? So indeed, this works, you need to impose this condition here, okay, in order to do this work in the standard way, all right? So once you have that, then the usual thing works, and then you get the result. But yeah, so there's a gap, right? So, I mean, in the result for survival for all lambda, you needed no moment, okay? I mean, you needed the first moment was infinite. I mean, that was the condition, and this condition for survival probability 0 at some small lambda positive. For that, we need a second moment. So there's a gap, all right? And the gap is when t has first moment, but not a second moment, all right? So in this case, this uniform bound to the first moment for infected intervals doesn't work. And all right, oops. Doesn't work, and the tunneling argument also doesn't work, right? Remember, the tunneling argument requires the intercure intervals to be increasing, right, in distribution to infinity, okay? So in this case, it doesn't work because I have a first moment. The first moment means that the intercure distribution is tight, all right? So you can't, so that won't work either. So we need something else. And so we have a condition, so not using any of those previous arguments, so it's going to be a sort of multi-scale recursion, but we need a condition for that. So this is more than a first moment, of course, because this function here is, so we were multiplying t here by e to the theta times square root of log t. So this exponential function here is slowly varying, okay? So it increases more slowly than any polynomial of t, but it grows faster than any polynomial of log t, okay? So this is, well, but we needed this, okay, for our argument to work. So this, I'm going to explain to you now the arguments for this, and let me just mention that we had a theorem like that before, but so we had stricter conditions. So we had so this is a sort of a newer result. So before we had 1 plus something moment, so larger than 1 moment for t. So this is not a big deal because, I mean, we weren't in this paper here, we weren't trying to optimize this condition here. So this is not such a big thing, but the other things are really more strict conditions that we required before, and now we don't. So we required d to be 1. So and also we had requirements on the regularity, extra regularity condition. I mean, regularity conditions on distribution of t. So it required it to be continuous and to have this decreasing failure rate. Okay, so this little f here is the density, so it's t is continuous, so it has a density. Little f is the density, and large f is the associated distribution function. So we require this to be, so this is the hazard rate or failure rate, I guess, and we require this to be decreasing, okay? And but now we don't require any of these, so we can have an argument in all for every dimension, and we know restriction on the distribution of T except this size condition here, which is really important. Here theta has to be large enough, okay? So, but fixed. So let me try to explain now how we prove this. So we need some difference argument. It's going to be sort of multi-scale. Hopefully it's simple enough so that I can explain to you how it goes. So the first thing we want to do is to relate the survival probability to, so survival probability is something that depends on all of the space, right? So in principle, so we want to relate that to something that takes place in a box, in a rectangle, okay? And so we will have rectangles of several scales, okay? A sequence of scales. So at scale n, our rectangle will have these dimensions here, 2 to the n and 2 to the n log n. So actually these dimensions here work under this more strict condition on the distribution of T. So let me just write what we actually stated, which is that this we stated that this is finite, right? But then in order to make this argument work with this condition here, you need a different scale. It's just that. I mean, it works exactly the same. So I just wrote things with 2 to the n log n. But okay, so this is slightly worse, right? Or well, it's worse, but it's still slowly varying, right? So so we want to relate the survival probability to the probability of crossings of this rectangle. So crossings here is crossings by contact paths, okay? Before I told you about infection paths. So infection paths are contact paths starting from some infected site, okay? So here we're dropping the condition that it starts in an infected site. So it's just a contact path, okay? It works the same as before except for this thing. So it's not really, so the crossings here are by contact paths, okay? Doesn't have to start from a infected individual, okay? And so the crossing condition is that either there's a vertical half crossing of this rectangle here. So vertical here is time, right? In the time direction. So space is horizontal and time is vertical, right? So moving up, okay? So either half crossing or a lateral crossing, okay? So it can be either from left to right or right to left, okay? There's a time orientation, right? But yeah, so it could be lateral crossing from right to left also. Okay, and so we have to give some initial condition here for on the bottom side of this rectangle, which this picture is in one spatial dimension, but I hope we'll see that it should work in general dimensions. But okay, so the okay, the initial conditions. So because of the initial conditions, we are taking here the soup over all the possible initial points for the renewal, right? So there are renewal processes here going on, right? Besides the contact bonds. The contact bonds are Poissonian, so you don't have to care about what goes on before, right? In order for you to have crossings, but you have to worry about the renewal. So I'm just taking the soup over all possible initial points here down, okay? Before this time. All right, so this is written here time 0, but I mean, in order to iterate this thing, we need just a generic time here, okay, fixed. All right. So we want to write now that the probability of survival. So in order for you to have survival up to time 2 to the n times log n, then one of these three things have to happen. So now we're talking about survival. So here, this is an infection path, right? So these three paths here are infection paths. That doesn't need to be a single one, but there can be many. But they start from the origin, right? We're assuming that only the origin is infected at time 0. So this is an infection path, and so it starts at the origin here from the center of this this baseline here, and so either it moves, you find a crossing here from bottom to top, starting at the origin, or the path has to move outside of the laterally to the side, either to the left or to the right side of this rectangle, right? So you see that in this vertical crossing here, you already have a comparison to Pn, right? So you get this first Pn out of this, and these two other crossings here by symmetry, their probability are the same. So you just write twice the probability of one of them. So now we want to make a recursion to the next scale down, okay? So we observe first that the existence of this lateral crossing here implies the existence of so if you chop now, if you cut this interval in half along this line here containing the origin, okay, you will see that, so since this is a lateral crossing to the right, you will find a crossing, left-right crossing here of this semi-rectangle, right? This half rectangle here. And this half rectangle has dimension 2 to the n minus 1, size 2 to the n minus 1 in this spatial direction, but in the vertical direction, that's time direction, it is 2 to the n times log n. So we want to reduce this to the right scale, right? So we want 2 to the n minus 1 log n minus 1. Okay, so so then you have to cut this. So we cut this larger rectangle into rectangles of the right scale, right? So it's 2 to the n minus 1 and 2 to the n minus 1 times log minus 1. And then you have this, you have to have you have this left-right crossing, but then it can happen in three different ways. Either one of these little rectangles will be crossed fully vertically, or you're going to find a lateral crossing of one of the smaller rectangles, or you're going to find a half crossing, okay, of one of these smaller rectangles. All right, and how many of these rectangles do we have? That's a simple calculation. We have order n of these rectangles, right? So you see after these considerations that you get a bound for this probability here, of a lateral crossing starting from the origin of the form of this form here, right? Okay, so you get this bound. So you get Pn minus 1 here from the fact that you have n that you have gone one scale down, right? Sorry, you have gone one scale down. All right, and the n here comes from the number of rectangles that you find. Okay. And so you get this bound. So in order to get that the probability of survival goes to 0 is just so that's what we want to prove, right? That's the survival up to a large time goes to 0 as the time increases. So so we can pick the sum as 2 to the n log n, and then it's enough to show that this this probability time, Pn times n goes to 0, right? So then that's what we want to show. So in order to show that, so we're going to set up a recursion for Qn, and then show that this, and then get the result from that. So this is, so yeah, sorry. So P, remember that P to the n has two components. It has two kinds of crossings. We just go back briefly. Oops, sorry, I went the wrong direction. All right, so Pn has two kinds of crossings. We have the half crossing and also the lateral crossing, okay? So now we're going to look only at the half crossing, all right? The vertical half crossing, all right? And the other one, the lateral crossing is treated more or less the same way. Essentially in the same way, all right? So this is a half crossing of the larger. Here I didn't put the full larger rectangle, just the half rectangle, all right? So it's 2 to the n. So I divide the big rectangle in 8 pieces. So the half crossing here goes over four pieces here, okay? And so you have a vertical crossing of all of these little rectangles here. These little rectangles, they don't have the right scale, right? So in order to relate this to the previous scale or previous scales, I will cut this, divide this. So I'm going to look at one of these rectangles, divide them in smaller rectangles, right? Four of them of equal size. And then observe that either, so there I have 5 possibilities here. Either you have vertical crossings of these half rectangles here, this first half rectangles, or this middle half rectangle, or the rightmost, or else you have to have lateral crossings of the even smaller rectangles, right? Smaller rectangles here, 2 to the n minus 2. Okay, so in this way, I mean, as soon as you have a so remember this vertical size here is 2 to the n log n minus 3, right? So this is larger than 2 to the n minus 1 log minus 1. Okay, if n is large, not very. Doesn't have to be very large, but you see that these 3 crossings here, they already give you a bound of the size of the kind Pn minus 1, right? Because then you're in the right scale, all right? So this 3 here comes from these 3. From these 3. Pictures here. But now the lateral crossings is more complicated. Well, it's not very complicated, but it's more complicated because now the vertical, so we want something in the scale 2 to the n minus 2, right? So, but this is far from this. So I have to chop things again, but you do it in the same way, okay? So in the same way, you can chop now much in the same way as we did, as we did here. Remember the chopping that we did here to adjust the scale, right? But now you have to chop more because it's 2 to the n minus 2, right? In here, it's 2 to the n minus 2. But then you get an n squared instead of n. And then and the other things work the same, and then you get a bound relating to Pn minus 2, right, with this factor of n squared because of the number of rectangles that you get when you chop, right? These little rectangles here in the, so that the vertical scale is right, okay, it's n minus 2 also. All right, so when you do this, you get this bound. And now, so now, so this is for one of these little rectangles here, but I have 4 of them, right? So I can, if they were independent, I could do what? I could raise these bounds to the 4th power, right? But they are correlated, but I can raise it to the. I mean, we can raise it to the 2nd power if we get out of the following event. So yeah. So I have to come back to this picture. So in this, so I'm going to look at crossings only of the 1st and the 3rd rectangles here, and for those I will use this bound that I just got. And now, in order to decorrelate these things, what goes on in 4th rectangle and 2nd rectangle, in order to do the so I'm looking at the 2nd and 4th, okay, not 1st. So what I'm going to do in the 1st and 3rd, I'm going to demand that there's no timeline here. We have 2 to the n timelines, right? I'm going to demand that no timeline here is completely empty of cure marks. Okay, as soon as you have all of the timelines here, at least 1 cure mark, then you get a decorrelation from what goes on in the past, right? Because it's renewal, right, with the independent renewals. So if you get a cure mark here, then you get a decorrelation from the past. Okay. So in order to demand this, you have to pay a price, right? And the price is the probability that you do have a gap, right? Like I just told you. And so after all, we get a bound which, well, if there is a gap, then you pay this price, p to the probability of having a gap. Otherwise, you can raise this to the 2nd power. Okay. So this is essential to raise this to the 2nd power because of this n squared here. And so now we have we do the same for the lateral crossings, right? This is just the temporal crossing, and we do the same for lateral crossing. And this is the last slide. So we get this recursion here, and now we multiply everything by n. Remember, we want to have n times Pn going to 0, right? So we get this recursion here now. So it's a trivial thing. So now you have to start the recursion with a small seed, right? So in order to be able to, because if we start small, then even though you have this polynomial term here, the Qn will be exponentially small, right? And it iterates, provided you can start small, right? And also provided you have a control over the probabilities of an. But because of this theta here being large enough, it's we get this control, and the probability of n decays exponentially. And so then you just use so far we didn't use the lambda, right? So lambda now is used to in the initial stage where you can make it so small that in the initial stage the probability of the Pn is going to be very small, right? I mean, if you fix an n and make lambda equal to 0, probability of having crossing is 0, of course, and provided you have the marks, right? So the Kira marks, and then it's a finite rectangle. This probability is a continuous function of lambda. So if you take it small, then you have it small initially, and then this thing iterates, and you get an exponential bound for Qn, and this closes the argument. Okay, so I guess that was what I wanted to say. Thank you.
Thanks, nice talk. Questions, comments?
Professor, in Theorem 3, you had some long time behavior for the infection at some site. And the only conditions you imposed that it was a renewal process and it has the alpha stability condition. My question is, do you need really that the process is renewal? Or it can be regenerative or...
So asking for more general
Yeah.
condition. Well, yes, that, I guess this is a good question. I mean, especially if you're thinking about some applications, I guess this would be probably one thing to look at. I'm afraid we didn't go beyond the not much. I mean, not at all beyond this framework that this situation here. So I'm not sure how things would work in a. So you mean with correlations, right, between the times, right? But in a regenerative way, right? Somehow, yeah. So I guess we don't. I'm not sure I can say anything about this.
Oh, okay, thank you.
Sorry.
More questions? No? No questions? Then let's thank again Ms. Renata.
I would be hoping so.
But I mean, yeah, I mean, it's not straight. So otherwise,
I can ask them to actually try to put it here while you're doing it.
yeah, sure, that sounds good.
Okay.
So,
I might try.
yeah, I mean, I was going to say.
Right. So welcome back, everyone. We're going to have the first session of exercise in Young Mills with Harpreet. Please remember that it was sent on the WhatsApp group, the PDF for the questions, and we're going to try to put them here as well. Oh, the floor is yours.
Do I need to use this or? I mean,
I
people can hear me.
no, it's because it's also being recorded.
Oh, okay. I didn't know that. So hi everyone. I hope everyone got the sheet that was sent in the WhatsApp group yesterday. So I think the aim would be to kind of discuss the first half of those topics. So the first thing that was there was kind of a symmetry argument, renormalization argument in rough paths. So okay, so let me recall the notation a little bit. So I write C alpha for the space of rough paths, and they are just from R to R. So with this map is currently C. So and okay, so X, and then so let me make a fat X, and that consists of these two components. And we fix alpha to be between 1/3 and 1/2 throughout. So, okay, so the first thing, microphone, okay. Do you have good technique to hold the sheet at the same time? Okay, so exactly. So the first thing that was on the sheet is kind of a natural renormalization group that you can define on here. So the group is given by, okay, G minus is just a copy of R. So with addition and 0 being the neutral element. And so, and G in G minus acts on a rough path by sending X, so this tuple to, so G maps this to kind of the same path in the first slot, and in the second slot you change it a little bit where these increments are just given by the previous ones plus this constant G times kind of the time that has passed. So, and then maybe one piece of notation which is useful is kind of we define by S. So S is a map which has two inputs. So let me just write it here. The details are on the sheet. So I think if I don't have to repeat all the notation. So it has two inputs, two functions, and then a rough path. And this is supposed to be the solution of the following SDE. Of the rough differential equation, which is given by, so y dy is f1 of y d, so dx plus f2 of y dt. And we fix some initial condition y0, and also we use the usual convention that the derivative that f of y, I mean, we want to solve it as a rough path, so we want to solve in the space of controlled paths, so we impose that the solution, so the Gubinelli derivative of the solution is given by f of y. So, okay, this is our solution map. And so, okay, so then there's a first claim on the sheet. So I don't know, I think it might be useful to have the sheet at hand at the same time. Then, okay, perfect. So I don't know, are there any questions so far, maybe? I mean, if there's anything unclear, please ask. Okay, so we have defined this solution map, and so the first claim is, okay, so what we can do is we have this renormalization group and kind of F1, F2, and we solve it with respect to some renormalized paths. So how can one relate this to the solution of the non-renormalized path? So the claim is that this is the same as if we take here the same function, and then here we have F2 plus G times dF1 times F1, and now we have no G up here. Okay, so to prove this, so I mean, just to have not to write down as much, I'll assume that F2 is 0, and then it's essentially unraveling the definitions. So the left-hand side then is given by, okay, the left-hand side corresponds to, okay, let's subtract the initial condition maybe. So, and okay, then this is the rough integral by definition of F1 of y of s ds, no, dx s. And we assume the second part to be 0. So, and now this is the limit where we go over partition of this interval 0 to t. So, and the partition size is going to 0 of, well, just the approximation. So uv, let's say, f of f1 of yu, and then the increment in x, so the first component, plus now the second term, which is given by d of f. Okay, and now here we will have the Gubinelli derivative of this guy, so which we assume to be f of y. And then here we have the increment uv, so the second component, and here we have a g. Okay, but then here we can just unravel what that means. So this is the same thing as in the front here, plus the same thing but without the g, so y f of y, and then u comma v without the g, and then we use that there's a last part which kind of this increment, so plus g times d f y f of y u minus v. Okay, and now we are essentially done. So if this first, if this part is a controlled path, then also it will be a controlled path for the changed rough path, and then by rough integration, this is the rough integral from f1 of dx plus, and the second term certainly convergence, since this we know is a continuous function, and this is just a normal Riemann integral then, so plus the integral of g times df f of y dt. So, and that's the claim. Any questions so far? Okay, so and then, so if we are given a smooth path x, there is of course a there's a canonical rough path associated to it, which is where x is just given by the iterated integral. So smooth. Okay, and then the claim is that if we are working with a smooth path, that actually the next claim that we want to show is that in the case of smooth paths, claim and we take the canonical lift, x canonical, then the solution map gives us the classical solution. So f1, let's say 0 again in the second slot, that doesn't really change anything. Canonical is the classical solution. And and for that, maybe let's just stare at this expression. And what we see is that here in the, so since the path is smooth, these will contribute, these are of size u minus v, and the iterated integral is of little o. So the observation is that u comma v is small o of u minus v. Actually, it is even of order u minus v squared, and therefore this sum, since the controlled part is bounded, this sum will not contribute anything in the limit as we take the partition size to 0. Is that clear, or should I elaborate a little bit? So it is neither clear nor I should elaborate. Okay. So, okay, and then kind of the last, oh, great. So can maybe change the side. I can do that. So how do I, okay. Okay, so, okay, that's, I already spotted a typo. Okay. So the last thing is that we want to show that claim that the map that we can define from C infinity to kind of C alpha, to rough paths and C alpha, the canonical lift does not extend continuously. And for alpha smaller than 1/2. So, and this time it's we take kind of so what we do is we look at kind of a 2-component path. So we define x1n to be of t to be given by sine of nt divided by by n to the alpha. So that's just the scaling so that this guy stays of order 1 in the C alpha. And we take a second guy, x2n, which is just the cosine, so the same thing with the same scaling. So cosine of nt divided by n to the alpha. Okay, and then what we see is that the canonical lift, so the integral, let's say from 0 to t, so of x t0 dx1n dx2, so r dr x2n. So that's just the integral of this guy, so the integral of sine of nt, and then the derivative of the second guy, which is again a sine modulo is -1, so this guy squared dt. And then we have these alphas, so we get 1 alpha from taking the derivative, 1 n from taking the derivative, and we divide by 2 alpha. And now, and since this guy converges to a constant, or I mean, let's fix t equals 1, this guy stays of order 1, and then this guy, n divided by n, 2, this expression goes to infinity. So certainly this cannot work. For example, we can like add a little epsilon here, and then we still keep that this goes to infinity, while this guy will go to 0 in the C alpha norm. So is this clear? So I'm very happy that few people are nodding, which makes life much nicer. So, okay, that was kind of warm up. So let me maybe change the slide and, okay, so in regularity structures, so renormalization doesn't to a large extent appear in rough path theory. I mean, one can cook up some examples where one actually has to renormalize. Otherwise, it's this kind of question of choosing Ito or Strantonovich integration. But somehow the renormalization that one does to go to Ito stays constant. And in regularity structures, there are kind of strong theorems shown by Martin Heyer and A.J. Chandra that under very general assumptions give criteria when the lift of kind of the renormalized model converges. So a model in this setting is the same as a rough path. And these things can be adapted. So one has kind of a black box now, which under very general assumptions tells us when things converge. And the idea of the next exercises is to show that if one has an additional symmetry, that then the renormalization constant cannot blow up. So maybe I clean the blackboard a little bit. So this I might keep since I want to keep the solution map there. Another thing that I mean, by now everyone must be aware of is that, I mean, the strength of rough path theory, or one of the main things, is that the solution map over there, that this map becomes this map is continuous if you take an appropriate norm on the two functions here, and then also on the rough path, you take the rough path topology. So next claim. So we start with a path x from R to R for simplicity. So all these things work exactly like this if you look at vector valued stuff as well, except kind of this continuity thing. So in one dimensions, kind of geometric rough paths are essentially polynomials in the increments. So that type of counterexample doesn't work, but otherwise everything works if it's RD valued as well. No, I mean, that doesn't work in one dimension, but I mean, for simplicity, if we look at R valued things now. Okay, so we look at a random path. And then we assume a symmetry, namely that X is time reversible. And what we mean by that is that X of dot has the same law as X of minus dot as a path. So, and okay, and then we also assume that there exists a family. Okay, so we define X epsilon to be just the mollification of that path. So, and we assume that there exists constants or G epsilon from in R, such that the map X maps to the lift the renormalized lift of this guy to a rough path. Okay, let me write it differently so that the renormalized guy, so we start at some epsilon mollification, then we renormalize the lift using this. So first we have a smooth path x epsilon, and we take the canonical lift, and then we apply an element of g to that path, that this thing converges in as a rough path. So okay, then the claim, so what then we look at y given by, so y dot equals, so y epsilon dot equals f of y epsilon dx. So here we have the non-renormalized guy. So so then y such that y is given by this equation, y epsilon converges to some random process y as epsilon goes to 0. And here we did not apply any renormalization or anything. So, and okay, here we should also assume that this is also not on the slide, that phi of minus x is the same as phi of x, so that the mollification preserves this time invertibility. So let me outline how we're going to do this. So the first step will be to, okay, we have this kind of sequence of renormalization constants. And the first step will be to show that these renormalization constants don't diverge. That is, that we don't find a subsequence that goes to infinity or minus infinity. Then once we know that the sequence G epsilon stays bounded, we argue that it actually converges. And once we have that it actually converges, then this claim follows. So I'm noticing, I don't know how you do it, but my hands are getting very tired from holding a sheet of paper and the mic at the same time. So, okay. So first claim is G epsilon stays bounded. And okay, when we show this by contradiction, and okay, either we find a subsequence that would converge to infinity or to minus infinity if this is not the case. So let's assume that it converges to infinity. Assume so, and I will leave out the subsequence in the notation from now on, but let's assume that G epsilon, so that means a subsequence goes to plus infinity. Okay, so then we look at the following thing. So we take F1, and then, okay, we take 0 in the second slot, and we look at the solution of this guy. So this is the renormalized equation. So on the one hand, from what we figured out behind, we know that this solves actually a classical solution, and we know that this, okay, we define, let's call it Z epsilon. So, and we know what equation this solves. So what we can look at is kind of this divided by the square root of G epsilon. And then what we know is Z epsilon. Okay, we define Z epsilon like that. Then we know that on the one hand, Z epsilon converges to 0 by continuity of this map, because we assume that this guy converges and G epsilon goes to minus infinity. So this this function also goes to 0. And then what we can also do is look at kind of the time inverted guy. So we define z epsilon in at time t to be given by z epsilon at time minus t. And what we find then is that what does this guy solve? It also solves an equation. So we look at time, the inverted guy, the derivative of this. Okay, that's just minus z epsilon, the derivative of z epsilon at the time minus t. And okay, so we know that this guy solves the classical solution. So this is just equation. So this is minus, okay, now the equation is given by z divided by this g epsilon. That's just this guy, and then we have an additional term from the renormalization, but since we are dividing by the same constant, the g goes away, and one has f of z df of z dt. And so, okay, let me maybe continue here on the side since there's still some space left. Okay, so what, and here we have an x dot. So, and this all is at time minus t. And what we find from the this assumption, okay, that tells us that x dot has the same law as minus x dot minus, which we now use. So this guy in law is the same as, okay, we just forget about this minus sign, so we have fz divided by square root of g epsilon x dot plus and minus now the other thing f of z df of z dt. Okay, but now we want to leverage kind of that we have this robust solution theory. So what we can do here is just add and subtract something. So we want to have f. So what we get that this thing is the same as f of z dx dot divided by square root of g epsilon. And there's everywhere there are epsilons hanging around. Also, it's z epsilon, but so okay, and then we want to here actually have a plus sign, since that expression we would recognize. So let's just add that. So we get a plus fz dfz, and okay, and then we have to subtract it twice. So we have f df okay, minus f. Okay, but the upper part we recognize as, okay, so this expression is the same as the solution map applied to, well, f divided by square root of g epsilon. And this guy, okay, and then we have kind of the rough path xg, the renormalized one, and that's this part, and then we have an additional term. Let me see if I messed up the minus signs. I don't think so. So here we get the minus f z df z. Okay, and then, I mean, so one thing that I also left out, okay, so here we have z's evaluated at time minus t, which are the same as then kind of the z inverse evaluated at t. So that's really the case. Okay, but now we are in quite good shape, since on the one hand, we know that this guy goes to 0. on the other hand, we also have stability of this thing, and they agree in law, so the time inverse of this guy agrees in law with this guy, and this guy does not go to 0 in general, since, okay, so this converges to the solution of 0, and then here we have some, so it's just an ODE. Comma, okay, X, and I mean, here we don't care since the first part is the only part where this acts on, so this is the same as if we put a 0. So this is in general, and I mean, if F are not degenerate, then this is really a ODE, and while the other thing is converging to a 0 or the increment. So that's kind of a contradiction to the fact that these epsilons could go, G epsilons could go to infinity. Okay, so now we know, and to exclude the case that they go to minus infinity, one argues exactly the same way. Are there questions? Okay. Thanks, Francesco. Okay, so what we know now is that these guys stay bounded. So now we can look at the solution to the following. So we define W to be given by, okay, the solution of, now we just keep a nonlinearity, and then for the drift part we put 0, and then again X, G, epsilon. Okay, and exactly the same calculation as we did before. So shows that the time inverse of this guy, so W inverse, has the same law as the solution of the equation. Okay, we again have an F, then we get this minus 2 dF F, and again the same path, X, G epsilon. Okay, and so now we know that this guy converges. Okay, so this guy converges to the solution of F, 0, no drift, and then G, X. That's kind of that's the assumption we put in, that this guy is actually converging. And a similar thing we get here. So this guy converges as well. And now they converge to two different rough differential equations. So, and now this can also not happen. So one in general would need a little bit of work to show this. But I mean, this certainly, I mean, is very unplausible that if we have two differential equations and random differential equations, and one has a drift, yeah, they're not the same equation in general. So yes, question? Oh, no, okay. So any questions? Okay. I feel like, I mean, it's nice if there are questions, and then we can discuss things, so don't hesitate to ask anything. Okay. Huh? Okay, so we're halfway, more or less. Okay, perfect. Okay, so this first part was a little bit about kind of, rough paths. So the second part is a little bit on geometry. So, namely, I want to kind of review the notions of principal bundles and kind of do some very basic calculations or manipulations. So, yes? Okay, so let me not remove it. Yes. Okay, yeah, so okay, we assume that maybe, yeah, I didn't explain that well. Okay, so we know on the one hand that this guy converges to this. One sec, so. Okay, so let's assume there are two subsequences that converge to two different things. Then, okay, I've confused myself again. So writing this up, I've kept confusing myself. So let me see what. So how did that go? Okay, so I mean, okay, I forgot to put the G epsilon here. Okay, now everything is good. So okay, if we have two subsequences that converge, then we would get two solutions driven by the same guy which are the same in law, but are two different differential equations. So if we had G epsilon converging to, let's say, G1 and G2, these are genuinely different equations that we would get for G1 and G2, but this guy converges to the same rough path. Okay, thanks for the question. So, okay, so the next part is a little bit on principal bundles. So let me also change the side on this thing. No. Okay, it's the wrong direction. Okay. So the setup, so principal bundles. So let's first introduce some notation. So we denote by P the principal bundle. Then we have this projection map pi, which maps to the base manifold M. And then we have a right action by a Lie group G. So, so this is the principal bundle. And then also to have some notation, we write sigma of P comma G for the right action. Okay. Okay, so sigma goes from big P cross G to P by definition, the right action. And let me remove this. Okay, maybe just to fix things in everyone's mind. So what's a principal bundle? So it's a G fiber bundle. So there are kind of two conditions. It's a G fiber bundle over M. So what the fiber bundle is essentially, you should just have the picture. You have a manifold and you attach to each point a copy of G. This can be somewhat in a non-trivial way. But then, okay. And then we have this projection map, and there are kind of two conditions. One is that pi composed with the right action, sigma, of, let's say, applied to P comma G. This is the same as pi of P, which gives us a point in the base manifold. And then there's also kind of a local triviality, local trivialization condition. So that is we find charts or maps that such that so around every point there's a neighborhood such of the manifold that the backwards image of this neighborhood is locally diffeomorphic to V cross G, and here the right action here is given by right multiplication. So So in this trivialization, local trivialization. So these are kind of the two conditions one imposes. Okay, so a last piece of notation for now is that, okay, so what's useful is to define sigma p as a map, the map that's just given by fixing, okay, of G, that's, or dot, let's say, that's given by sigma of, we fix the first slot and we let, leave the second slot open, and sigma G of dot, it's useful to have as well. So that's the same thing, but this time we fix the element of G. So it's just the right action on the bundle. Okay, so given this data, there's already one canonical subspace of the tangent space of P, so which has a name, so the vertical space, well, which we denote by VP at the point P. This is given as the kernel of the projection, derivative of the projection map. So at P, and that's a subspace of the tangent space of P at the point P. Okay, so if you have the picture, so up here you have somehow your bundle and you have this projection going down. So these guys are all the things that kind of look in the direction of G as you would act on the other group. So, and this we will also make more rigorous now, but okay, so so the first claim that we can show here is that, namely that, okay, we can act, so we can act on this vertical space using the group action. So if we act by G and on the vertical space at P, that this thing is just the same as the vertical space at P acted on by G. Okay, and P dot G here is the same as sigma of PG, but it's more convenient to write, and this is sometimes called G equivariance. So, and it's really this picture, okay, we have the space. Yes, so this is the derivative of the map, which, okay, so if you have two manifolds, the derivative is the thing that takes a tangent vector from one manifold and gives you out a tangent vector in the other manifold. So which in charts then is just the usual derivative matrix. Any other questions so far? I mean, yes. So this is the convention, but of course, I mean, you can always turn a right action into a left action, then many things would change. But I mean, yeah. So this is the usual convention, but it's not, doesn't have any deep meaning. So okay. Okay, we want to prove this claim, namely if we have our vertical space, we map it, and kind of pictorially, this, I mean, it's really very clear, and kind of to show it, we start with a vector. So we start with X, a vector in the vertical space at P, and then we want to show that if we act on it by d sigma G, that this is in the kernel of this other guy. So then we have that the dpg, so we want to act with of the projection map, okay, acted on sigma G at P of acted on X. Well, this guy is just the same as the derivative at P of the composition pi and sigma G. Okay, and this is just the map pi. This is the acted on X, but we know that by definition, dp of pi acted on X is 0. So actually we have one inclusion, and then by dimensional considerations, since we know okay, so this local trivialization part tells us a lot. So what we also have is that this sigma map is a diffeomorphism of each fiber. So if we have one inclusion in one direction and we have that fact, then we get that this is actually they are actually the same spaces, simply have the same dimension.
Sorry.
Yes. Yes. Okay. So yes. So this is just the chain rule, so that the derivative of a composition is just the derivatives composed.
Yeah, that's fine. But then, why is the derivative of the second thing evaluated at x0?
I mean, acted on x0. Okay. I mean, they can make another bracket. So. Yes, so I mean, the space, the VP is defined as the kernel of this guy. So these are all the vectors that are kind of parallel in the G direction, if you want to think of G inside of P. And yeah, and they are kind of projected away. And that's kind of the definition. Okay, so we have this notion of a subspace. Then there's a notion of a principal bundle that we have also seen in the lecture. So principal connection. And a principal connection is a collection of subspaces HP, which are horizontal. And that just means that HP direct sum with VP gives us TP. So these are subspaces. So that's the condition of being horizontal and G equivariant. Okay. Okay, then the next claim would be that one can always construct such a principal connection. So, principal connection always exists. And I mean, this is really kind of a standard-ish argument. So, so the first naive attempt would be to kind of, okay, we give us some subspace like that, and then you would like to patch them together. But this, I mean, somehow not clear if you go around the circle that somehow you can construct exactly the same thing. But on the other hand, you can always construct a Riemannian metric on any manifold, because somehow metrics you can just add. And this is actually what you do. So what you can do is you can locally certainly construct a metric which is invariant under the action of sigma, so under the pullback under sigma. So you get and then given that metric, you just take the orthogonal complement. So you have these metrics on each of these, and you just patch them together, and then you can take the orthogonal complement of the space VP, and that gives you that things. And since they are really the same under the action, they give you actually something that's G equivariant. So that's kind of the outline on how one can do that. Okay, so then the next thing that we want to look at, okay, so for X in the Lie algebra of G, so are there any questions so far? Okay, yes. So what we want to find is a G invariant variant scalar product on -1 of some neighborhood of this guy. And since we can add up scalar products, we can patch them together. So kind of just adding them in different of these neighborhoods. So patch together, and then we can take, with respect to that G invariant scalar product, we can take the orthogonal subspace H to be. Okay, any questions? So the next thing, so we have this Lie group, and then we have the Lie algebra, which is just a tangent space at the identity. So what we can define is kind of something called the fundamental vector fields sometimes. So which we write X, this symbol, which is given by AP of X, and we want to define AP. So AP is kind of the infinitesimal action of the group, if you want, at P. So, and that's where AP is the same as the derivative of sigma P, which maps at the identity, which maps the Lie algebra to the tangent space at P. So what you should think of is, okay, if we take something in the Lie group, so what that does, it kind of moves things along the fibers. So this AP does that kind of in the infinitesimal sense. So it gives, for each Lie algebra, it gives us kind of the vectors in the direction of G. Okay, but this is just definition. So, okay, another claim is that AP maps maps G to the vertical subspace. So that this intuition is really the correct one, and this is a linear diffeomorphism. An isomorphism. So, I mean, since kind of this action by G is anyway, so the main thing that we have to show is actually that this statement is true. Since it's anyway a diffeomorphism onto the fiber. So G, this map that's given by multiplication maps G diffeomorphically to the fiber over the point. So, and this is again the similar kind of calculation. So what we want to look at is P, so the derivative is that P of composed with AP, but that by definition is just the derivative of P composed with derivative at the identity of the sigma P. Okay, now we use the same trick as before, not really trick. So this is the same as a derivative at the identity of the Lie algebra of pi composed with sigma P. And this guy is always constantly sigma pi of P. So therefore this guy is here. Okay. So let me. So can I ask what time it is? Again? 10. Okay. So, okay, maybe I can add something in here between. So, what's a connection one form? So, a connection one form is so let's write omega. This is a one form from on P, so with values in the Lie algebra math frac G. So, and such that the following conditions are satisfied. So let's say A, namely if we take omega and apply it to these fundamental vector fields that we have defined above, or on the other page, so then this is the same as X. So what that just means is kind of, if we think of these fundamental fields really being copies in P, so then the omega doesn't do anything to those vectors. And then there's a equivariance condition, namely that sigma, if we push sigma forward, this is the same as add G to the, composed with omega. So, which here, this is just the derivative of the conjugation map, which is the adjoint action on the Lie algebra. Okay, so this, let's call this B. Let's see if we, okay, so that's kind of just this slide. So, and then, so then there is now kind of a canonical one-to-one correspondence between these principal connections, which are these subspaces, and these one forms. So the claim would be so if omega given a principal connection that's this collection of subspaces, which is G equivariant, then we can define a one form. Okay, and that one form is defined by taking omega p of kind of a vertical part plus a horizontal part, which are now given since we know what the subspaces are, and then we look at the applying the inverse map AP, and we cannot, I mean, this is not surjective, but we can apply it to a certain part, and that's the vertical part. So, okay, the claim is that this is a principal one form, is a connection one form. So are there questions for this statement? So kind of the picture you have in mind is that, okay, we start with these subspaces, then we have kind of these canonical AP maps, which relate our Lie algebra to a subspace in the principal, to the tangent space in the principal bundle. And what we can do is, and we know that these are isomorphisms onto the vertical subspace. So what we can do is, if we want to evaluate this guy, we can just look at the vertical part. That's characterized by the fact that we have this direct composition. So taking a different direct composition would give us a different VH, so it would change this expression. And then we map back. So is that, okay. So, and now we want to check the two conditions, A and B. So, and A is satisfied essentially by definition. So, okay, so by definition, we have that X is given by AP of X, and therefore this condition follows directly. Then the other condition, for that we have to do a little bit of more work. So what we look at is kind of the pullback under this action of G of the form at some point P in the principal bundle, and then we want to apply it to the vector which has a vertical part plus a horizontal part. And then by definition, this is the same as omega at the point PG applied to, now we apply sigma to these vectors, so the derivative of sigma, the sigma G applied to V plus the same thing applied to sigma G applied to the horizontal part. Okay, but so if we take anything that is already horizontal by kind of the definition of a principal connection, if we shift that vector, that will stay horizontal. So this is one place where, this is the place where the G equivariance of the subspace, of the horizontal subspace comes in. So then, since this guy is horizontal, this is just omega PG applied and to d sigma G of the vertical part. Okay, so let me continue here maybe. So now we want to have a closer look at this guy. And what we know is that we can write the vertical part as AP of some vector X in the Lie algebra. And then the left-hand side here, so then what we are calculating is omega PG applied to the sigma G AP, and AP was just the same as d sigma P, and we apply this thing to X. Okay, so let's look at what the map sigma G composed with sigma P does. So this maps, so we take a point X, so we apply sigma P, so X is in the Lie group, and that's just the right action. So we get P times X. And then after that, we are applying sigma G, which is again acting by G on the right. So this is this expression. So, and that we can rewrite as P, PG, G to the -1 X G. So, and therefore, we can rewrite this thing as, okay, by definition, this was the same as the horizontal, so this is AGP, PG, to the -1 applied to the D, and now we use this back. So this is the same as applying conjugation by G to the -1 and composing it with sigma PG and applying that to the point X. So, and using this identity, so that this map is the same as this map, we can rewrite this expression as sigma PG composed with D conjugation, so the conjugation map, the derivative of the conjugation map applied to X. Okay, by definition, this is the same as APG, so these guys cancel, and we are left over with the conjugation map applied, the derivative of the conjugation map, which is just this adjoint map, G to the -1, applied to X. And now what was and this is the same as the by definition of x, p to the minus 1 applied to a p to the minus 1 be the vertical part. And that is what we wanted to achieve, which unfortunately I've removed, but that's the last equation on the board. So do I have another moment or? Okay, so, I mean, are there any questions? At least for me, reading these computations for the first time, it was very confusing. So, I mean, please ask. It's not. Okay, so the next thing that I wanted to quickly introduce, which is also, I think, very good for general culture, is kind of the notion of a Maurer-Cartan form. And I think, so what time do we actually, okay. So, I mean, I can continue at this point, Nick. Or, yeah, I mean, so, okay, I think we can also end here. People are probably hungry.
Thank you very much, Harpreet. Are there any questions? No? Well, if not, oh, sorry.
The question is simple. Can you tell us, in 3 words about more time?
Yes, so I mean, yeah, we want to get the country space at some point, and what is the derivative of the multiplication by that? So you want to take x's in the algebra back to the origin, which is the, I mean, for the real algebra, it's kind of the origin, and you want to take country space at different points and back to the
Are there any other questions? Well, if not, let's thank Harpreet again.